Today, looking at periodic trends. So 4 trends you need to know: atomic size, ionization energy, electronegativity, and then reactivity. And there's 2 trends here for reactivity we'll look at. The first one, atomic size. So this is just how big an atom is based on kind of that outer electron. There's a few different ways they measure it. We'll just say it's from the outer electron. All of the trends you're going to see me draw, or that are drawn, this is in increasing. So atomic size increases as we go this way and as we go down. So your largest atoms are going to be here, smallest atoms up here. And we'll talk about why in a little bit. The second one, ionization energy, you'll see me abbreviate it IE because that's a lot to write and I'm lazy. Again, increasing, but this time it's opposite. So ionization energy increases as you go up, increases as you come over here to the right. So the highest ionization energy, and ionization energy is how easy is it to pluck off an electron so you get a positive charge. So if you think of it in terms of that, this will hopefully make a little more sense once we talk some more about it. But how easy is it to pluck off an electron? It's easiest down here. It's hardest up here. That's why it's so high. It takes a lot of energy, high energy, to get an electron off of something up here. The next one, electronegativity. This is how much it likes electrons. So how much pull does it have towards electrons? And this one, it's the same as electronegativity, if you want to think of it that way, because it's the opposite in terms of chemistry. So here, it increases as we go up here. And again, for a lot of these, especially electronegativity, we're not talking about the noble gases. Especially for electronegativity, you can kind of forget those noble gases. We're talking fluorine has the highest electronegativity value. Fluorine will steal electrons from absolutely everyone, even a noble gas who doesn't form compounds. Fluorine, he's the bad boy. Super small though, so short man syndrome maybe, if you want to think of it that way. Reactivity, 2 trends here. You have one for metals, and metals we're talking usually about alkali metals and the alkaline earth metals. As you go down that column, down that group, it increases. For nonmetals, again, we're not talking about your noble gases. We're really talking about those halogens, so something like fluorine, and even oxygen and stuff up here, but reactivity increases up here. So these guys towards the top going to form a lot more compounds because they're more reactive. And we'll look at these trends more for reactivity especially, because that's a fun one to look at. The other big point of this is you need to know why these trends occur. So not just that they occur. It's an honors class. You need to understand why. So all of these trends are influenced by 3 factors. The first is energy level, or what circle are you in if we're talking the Bohr model, or if we're talking quantum mechanical, what's your principal quantum number? Is it 1 and you're super close to the nucleus, or is it 5 and you're further away? So higher energy levels means the electrons are placed further from the nucleus, meaning they're further out. Nuclear charge, then, think of that, it's just the number of protons in the nucleus. The more protons you have there, the more pull you're going to have. And then, so some of these, a couple of them come into effect. And it's a tug of war, who wins type. The third one is shielding or blocking, however you want to think about it. But here, the inner layers of electrons, so like these electrons here, are blocking some of that, if you want to think of it that way, are blocking some of that charge from getting out to maybe this guy out here. So it keeps that positive charge from reaching, you know, these outer layers of electrons. Or again, Bohr model is easier to think about, but same thing in the quantum mechanical model. Those weird shapes are just stacked upon each other. So same thing. You know, your outer S and P and D and F orbitals, you know, they're further out here. That positive charge can't reach them as well because of those inner ones. And then the last part, so we talked about those three trends. What did these factors influence? So energy levels and shielding affect group trends, or up and down on your periodic table. Now, the further you go down, the more energy levels there are. So the more energy levels, the more shielding that's going to happen, because you're getting those electrons further and further out. Here, it's going to make those outer electrons easier to pull off. That's why ionization energy is high for the top part and low at the bottom. It's easiest to take them off at the bottom left. Nuclear charge affects period trends. So this is the only one that affects left to right, because for this, if you have, let's take an easy one for example. We look at the Bohr model, and we look at, so let's look at lithium. Well, lithium, 1 electron in the second ring. As we go across that periodic table, so I got to look here, beryllium is the next one, so it's going to have 2 electrons here. As we go across that row, to beryllium, and then from beryllium to boron, notice where I'm putting the electrons. I'm putting the electrons in the same ring, so those electrons aren't quite as far out maybe as if I have to jump rings. Well, not jump, but maybe, if this one fills up to 8, 5, 6, 7, and 8, well now that next electron has to go out here. So think of it that way. But if we are looking at those, to finish my thought, those electrons going in the same ring, so this would be with 5 electrons. 5 electrons is boron. This nuclear charge, well, as we add 1 electron, we keep adding 1 proton. So the electrons are going in the same shell, but then we're also adding more positive charge. So we're adding more pull to the middle. So that's how nuclear charge affects period trends, or left to right trends. Electrons in the same ring, but you're adding more positive. So there is more, negative. There is more opposite attraction. We'll talk more about these. We'll apply more of these, but I just wanted to give you the notes, and then we'll look at these definitely more in depth.